Okay, the next one is quite similar. It's testing basically an exact Poisson rather than an approximate, rather than an exact binomial like in the previous problem. And so basically it says that last year we received 520 web hits per day. Important, remember that's per day. In the and then in the first 30 days of next year, the website received 15,800 hits. Assume that the web hits are Poisson, and we're kind of conditioning on last year's web hits as 520 per day. And the question is, are we up? Are we doing better? So we want to do a Poisson test. So we want to test the null hypothesis that the rate is 520 per day, that lambda is 520, versus the alternative hypothesis that lambda is greater than 520. So all our calculations are going to be done assuming a rate of 520 per day. So we want p-pois for the Poisson probabilities, and then remember this, we have this lower dot tail thing, so we want 1,500, 800 minus 1. This minus 1 is going to make no difference whatsoever in the value, with the exception that it might mess up the auto grader because I asked for 4 significant digits. So it's a very pedantic thing to put the minus 1 in there. We know that the Poisson probability, when you're out that into numerals that high, that whether or not you add or subtract 1 is irrelevant. But we're doing it anyway because we know the auto grader will mess up if we don't get it exactly right. Okay, so 15,800, and then our lambda is 520, but that's per day. And here we said we monitored it for 30 days. Okay. Oh, and I forgot my lower dot tail. Lower dot tail equals false. Or I could have just 1 minus that other number. Or actually that would have been wrong because of the minus 1 thing. So we get this number right here, 0.055. Okay. And then does it reject? So no, it technically doesn't reject, because if we're using a 5% type 1 error rate, so I'm going to put a 0 there and submit. And it's again giving me the incorrect answer for the 0, but it's, of course that's the right answer. So again, it's that same JavaScript error as the previous time. So I'll double check on that and see what's going on. See, now it's put in 0 and says it's correct. So I'm not 100% sure what's going on there. I'll look into that. My coding skills for that sort of stuff aren't that great, but I'm confident I'll be able to figure it out at some level. Okay, so let me just show you also how to do a normal approximation. So as your Poisson mean gets larger and larger, your Poisson is going to be better and better approximated by a normal. So remember, the mean of the Poisson distribution is lambda times t, and the variance of the Poisson distribution is lambda times t. So why don't we do p norm, the probability of seeing, and let's just forget about the minus 1, especially because it's a normal calculation. We're already doing an approximation. So we want that number, and we want it the mean of 520 times 30, right? And the variance is 520 times 30, which means the standard deviation is square root 520 times 30. And we want lower dot tail equals false. Okay, and it gets pretty good actually. So that's up to 3 decimal places, 0.055 for both the Poisson and normal approximation. Okay, so probably in most cases, I think if anyone had counts as high as 16,000, you wouldn't bother doing the Poisson. You wouldn't bother doing the Poisson. You would just use the normal approximation. That would be the most common thing to do in that scenario.